and welcome to this lecture. In this lecture, we are going to start looking at functions of a continuous random variable. Okay, so you see that just like we did a whole bunch of things for the discrete random variables, we are going to do the same thing for the continuous case also. You'll see in most cases, it's sort of similar. What you did with the PMF in the discrete case will sort of happen with the PDF. But things get a little bit more confusing because of some integration and all that. So people get a little worried and they have to think about it very carefully. That's all. I mean, it's if once you have some practice, you will get your hang of it. And this fact that you have to use the PDF and keep integrating it to get the probability, something to get used to. But once you get used to it, it's very easy. Okay. So now let's see functions of a continuous random variable. Now, why functions? You might say, already I have a random variable, already have its PDF, already have its CDF. Why do you want to make a function of that random variable? It turns out here is, I've thrown a couple of very simple situations. In reality, you'll have so many other cases where functions show up very naturally, right? For instance, you may model the length of a square as a random variable x. Okay. Then if you want the area of the square, it's going to be x squared, isn't it? So you don't need to have a new random variable for it. It's a function of the previous random variable. Same thing with say volume. It's not volume occupied, right? This is wrong. This is weight. Okay. So supposing you have density being a constant for some liquid rho, and then you don't know how much of that liquid is going to come in. You want to find its weight. It's density times the volume, isn't it? So you see that there are very simple functions. You model something as a random variable. There are some very simple functions of it, just a scaled version, or maybe even addition of something to it, or the squaring. Okay, simple functions like that. And it's good to know how to find the distribution of the function of a random variable. You're given the PDF and CDF of x. How do you find the PDF and CDF of x squared, right? Are there very simple, straightforward methods? So this is like a skill that you have to pick up. Why is this skill important? Because quite often this will happen. You will have one thing that you can model easily as a random variable, but actually what you're interested in is some other function of that. So how do you go from here to there? There is a very standard way to do it, and let's see what that is. Okay. So I'll begin by giving you simple examples and motivating the method, and then we'll see a very general example, and we won't we will see a general enough way of tackling it, but I won't give you too many examples and confuse you too much, but you'll see some interesting things can happen when you look at functions of continuous random variables. Okay. Let's start with the easy case. Okay, so let's say x is uniform 0, 1. Okay, remember what is x is uniform 0, 1? PDF is 1 by 1, right? So it's just 1 between 0 and 1. Okay, so it's the uniform distribution between 0 and 1. Okay, let's say you want to look at y equals 2x, 2 times x. Okay, so this is going to belong to the range 0, 2. Okay, 0, 1 was your uniform distribution. Now you do 2 times x, you can go to the range 0, 2, right? Now what is the distribution of x? Or distribution of y, I'm sorry. So intuitively you might guess that y maybe is going to be uniform, right? But you would like to have some proof for that, right? So maybe y is uniform in 0, 2. It seems intuitive, but how do you write down and how do you prove it? It turns out it's not very hard. It's very easy. So you take a small y between 0 and 2, okay, and try to find the CDF of capital Y, right, evaluated at y. So basically f capital Y of y. So now this is a crucial idea. You have to go after the CDF of the function first. Okay. So once you do that, you'll see everything will fall in place. Okay. What is the CDF of y evaluated at small y? It's the probability that y is less than or equal to small y. Okay. Now you can use your function substitution. Y is 2x, isn't it? Capital Y is 2x. So y less than or equal to small y is the same as 2x less than or equal to small y. Now bring the 2, you sort of invert the function. Instead of 2x, you can say 2x less than or equal to y is the same as x is less than or equal to y by 2, and that I know how to do, isn't it? I know the PDF, so I simply integrate the PDF from 0 to y by 2. I get y by 2 as the CDF of y evaluated at small y. Okay. So notice how I did that. So remember, fx of x is just 1, Okay. So it's just integral 0 to y by 2 1 dx, and 1 is just x, isn't it, x between 0 and y by 2, so it is just y by 2. Okay. So that's the CDF of y. So you always find CDF first. Okay. So this is an important trick. So find CDF first. Okay. So it's a very basic trick when you want to deal with functions of a continuous random variable in particular. Okay. So once you have the CDF, you can differentiate it and find the PDF. Okay. So you take the derivative of the CDF, you get the PDF. So y by 2 is just 1 by 2. So the PDF of y is actually flat again, it's just half. For any value of y, it is just half. So you see from that y is uniform 0, 2. Okay. A simple basic little derivation to tell you what you intuitively knew, that when you go to 2x with x being uniform and just scale it, you're going to get another uniform distribution. Okay, so that's not very bad. And here is a pictorial representation of what happened. You had a x which had a PDF from 0 to 1, and now when you did 2x, the height reduced by half and the width went from 1 to 2. Okay, so it went from 1 to 2 and the height reduced by half. Okay, so that's what happens when you do this kind of scaling. Okay, you can also ask some question like, instead of y equals 2x, what about y equals x plus 2? I don't know, x plus 5. Okay, or y equals 2x plus 5. Okay, so you can guess intuitively by going through the same method and repeating it, etc. Any such transformation, any such affine transformation, ax plus b, right? So y equal to ax plus b generally, right, is also going to be uniform in the suitable range, right, from 0 to 1. So it's going to be b to b plus a, isn't it? Assuming a and b are positive, for instance, right? So that you don't get into trouble here. So y is going to be uniform here. So this is a sort of a general result you can have for uniform distributions. So that's hopefully that tells you that that there is an easy way to find the CDF and PDF for the functions of a random variable. It doesn't seem too difficult. You have to just write down the formula for the CDF and convert from y to x, right? So that seems to be the method. So let me just summarize that in general what you do. Okay, supposing you want to have a random variable x with CDF capital Fx and PDF small fx, and you want to find the CDF of a function of x, g of x. Okay, g is a function. It has to be a reasonable function. I mean, most functions that we consider will be reasonable, but it turns out there are very unreasonable functions in mathematics. But anyway, so let's not worry about that too much. So g is a good function, nice function. You can take it as a very simple function if you like. So y equals g of x will also be a random variable once g is a reasonable function. It will have a CDF fy, and how do you determine it? This is what you do. Fy evaluated at small y is probability that y is less than or equal to y, and that is probability that g of x is less than or equal to y. Okay. So now this g of x might be some function, okay, I don't know, some function like this, and then you have a value of y here, which is maybe this guy. Okay, so this is y. Now, what is g of x is less than or equal to y? This is x versus g of x. If g of x has to be less than or equal to y, you have to look at the set of all small x such that g of x is less than or equal to y. So you see this guy, you see this guy, all this part and all this part corresponds to this set. Okay, so these two together is the set of all x such that g of x is less than or equal to y. Okay. Now, my probability that g of x is less than or equal to y is same as the probability that x lies in this part, in this set, right? If x were to lie in this set, g of x will be less than y. Okay. So that's the idea. For every y, as you keep varying y, this set will also vary, right? So if this y is going up or coming down, okay, as this y varies, this set will also vary. Where it hits the g of x will vary, the set will vary. So the probability of y less than or equal to y, or probability that g of x is less than or equal to y, will keep varying, and it has been converted now into a problem of probability for x, isn't it? Of an event defined using x. Okay, for x you have PDF and CDF, so you just simply integrate the PDF over the intervals which are valid for you. Okay, so this is the general idea. You find the CDF. Once you find the CDF, if it's differentiable, you differentiate it, you will get the PDF, etc. Okay. So how to evaluate the above probability? You look at the subset AY, which is set of all x such that g of x less than or equal to y. It will depend on y, right? As you keep varying y, remember that picture, as you keep varying y, the set of all x for which g of x is less than y varies. Okay, so you convert it into intervals in the real line and you find the probability that x falls in those intervals, either using the CDF or using the PDF. Okay, so it's just the integral over this AY of the PDF. Okay. So if Fy has no jumps, it is continuous, etc., you can maybe differentiate it and find the PDF also. Okay. So this is the general method. For any function g of x, this method will work. Okay. And this is what I did, I showed you in the previous thing. It may be a little bit laborious, you might have to, this inversion, right? This inversion process can be a bit painful, right? You need to know the function g of x properly and then do the inversion. Once you do the inversion, the calculation is straightforward. It just involves the integral of the PDF. Okay, we will see a few examples towards the end of this lecture for this method. Okay, there is a special case which gives you a direct formula. So we all love formulae, right? So if there is a direct plug-in formula, there's nothing like that. That's what I want. I don't want all this complicated method of CDF and integration and inversion and all this. I just want a formula. Okay, so if you want a formula, then it works only for a certain special type of G. Okay, in particular, if G were to be monotonic and differentiable, okay, so monotonic and differentiable, it's either increasing or decreasing, okay, so it's invertible, it has a clear inverse, okay. If that is true, right, and it needs to be true only when, for the x in support of capital X, I'm sorry, this has to be capital X, okay, maybe I don't need to make it so hard, I'll just make it capital X. Okay. In the support of capital X, it has to be monotonic. Okay, so monotonic meaning either increasing or decreasing. It cannot do some crazy thing like that and all that. It should be invertible and all that. So and it has a derivative. Okay, so d, you can differentiate g of x and find its derivative g prime. If you do that, then the PDF of y itself has a direct formula. Okay, and that formula is given here. You have to find g inverse of y. Okay, so if g of x is monotonic, and in a certain range, you can find g inverse of y. Okay, so you just, how do you find g inverse of y? Write y equals g of x and solve for x in terms of y. If you can do that, you have the inverse. Once you have the inverse, you can just plug it in into the formula, right? So fx of x is the PDF of x. Instead of x, you put g inverse of y. Okay, I'll show you an example. You will see how easy it is. And then notice what is going on here. There is a 1 by absolute value of the derivative. In the derivative also, instead of x, you put in g inverse of x. Okay, so remember, what is this guy? Fx of x, you put, instead of x, you put g inverse of y. Same thing here. So this guy is g prime of x, instead of x, you put g inverse of y. Okay, so you plug that in, you find g inverse of y. So finding g inverse of y is very crucial, and it having a derivative is also crucial. If all these conditions are true, you can easily have a formula. So I'll show you examples. I'll show you 3 examples. The first is y equals x plus a. So this is g of x, right? So this is g of x. So g of x equals x plus a. So what is g prime of x? G prime of x is 1, right? The derivative is 1. What is g inverse of y? So if y is x plus a, x is y minus a. So g inverse of y is y minus a. Okay, so this is how you go about doing it. This is how you mechanically use the process. And now you substitute it into the formula, right? So fx of x is whatever. Fx of x, instead of x, you put g inverse of y, y minus a. And then there is a 1 by derivative, but derivative is just 1. It doesn't matter what value you put in here, it's 1. So you get fy of y is fx of y minus a. Okay, so you can see why that is true. So if you have a certain distribution for x, and then you're taking y as just x plus a, it is just the PDF shifted to the right by a, right? So you take the original PDF, you shift it to the right by a, you get the new PDF for y. Okay, so translation, is very, very easily dealt with using this formula. So what about scaling? So scaling, g of x is a times x, okay, g prime of x is a, okay, and then y equals ax implies x equals y by a, so g inverse of y equals y by a, okay, that is the idea. So I put x by a here, this is again wrong, y by a. So in all of these things the support has to be capital X, okay. So this is fx of y by a, and notice what happened here, it became 1 by mod a, okay. So the absolute value will come in here. In the previous case the absolute value did not come in because derivative was just 1, it is always positive. Here a could be positive or negative, okay. So you have to put the absolute value will actually enter the picture, you will need absolute value of a, then fx of y by a. Okay, so you see translation and scaling. So these are very basic operations. Any random variable you have, you may have to move it around, you may have to scale it. Okay, both of those are easily handled by this formula, monotonic differentiable case. You don't need any CDF or anything. You can use CDF also, you'll get the same answer. But here is a direct formula for what will happen to the PDF when the scaling or translation happens. So for instance, if a is 2, you're getting fx of y by a. So fx gets spread out, right? When you scale it up, the random variable becomes larger, and the original PDF sort of gets spread out over that range. So it's a sort of natural and simple in some picture, right? So maybe I should show this. So if you have, for translation, if you have a certain fx, which maybe is like this, and you move it to the right by a, you will get fy, it will go off somewhere there. Okay, so you can maybe keep the x here, this is fx, and this guy is a. Okay, so you push it to the right by a, that's translation for you. And notice what happens in scaling. So maybe I should draw both in the same picture. So if you have fx, if you do 1 by a, fx of y by a, if a is greater than 1, you will get something like this, right. So this is for a greater than 1. For a less than 1, it will sort of shrink, okay. So it will shrink for a less than 1, so it will go like that. So this is a less than 1, okay. I think the picture became a bit messy, but hopefully you can see that. So what will happen? So there is fx of x, and then fy of y is becoming fx of y by a, and then it gets divided by a. So if a is greater than 1, it will go down and it will spread out. If a is if a is less than 1, it will shrink and then go up. So that's sort of how the picture looks for scaling and translation. Let me make my changes here so that the slides come out okay. Okay, so now you can combine the two. Okay, so ax plus b you can do. This is a very common operation. It's called the affine function. You had a, you had ax, you had x plus b. You can do one after the other, and you can combine the two formulae to get 1 by mod a fx of y minus b by a. Okay, I'm not going to illustrate what happens here. Things move around. Things move and then get shrinked or blown up a little bit. That's what happens when you do an affine transformation. So given a distribution, you should be able to easily visualize what happens under affine transformations. So affine transformations are very, very common, and this monotonic differentiable function method directly gives you what happens to the PDF when you do affine transformation. Okay, translations, just move the PDF around. Scaling, either scale it down and spread it out, or sort of shrink and increase in value of the PDF. Okay, so this is a simple example. There are of course so many other monotonic differentiable functions. Okay, affine is just one example, but it's a very popular and important example for you to know. So we've kept it there. Okay, now let's come back to this affine transformation of random variable, of normal distribution random variables, right? Supposing x is normal with mu equals 0 and sigma square equals 1, right? So you remember this is the famous normal distribution. This is mu and this is this is mu equals 1, and then let me not use mu here, this is 2 parameters, this is the standard normal, right. Okay. So, this is the PDF for the normal distribution 1 by root 2 pi e power minus x squared by 2. Okay. Now, if you do the transformation y equals sigma x plus mu, this is an affine transformation. Okay. And one can now use the formula, right, is ax plus b. So, it is y minus b by a, right. Instead of x, you should put y minus b by a. So, instead of x, we put x minus mu whole squared by 2 sigma squared. So, instead of x, you put replace x with I mean, I've put x here, maybe I should have put y, maybe I should put y here, sorry about that. Replace x with y minus mu by sigma, okay. You get e power minus y minus mu whole squared by 2 sigma squared, and then there is a 1 by mod a, isn't it? So, let us say sigma is positive, okay. So, there is 1 by mod a, and that is where the 1 by sigma comes in, okay. So, this you can see is the PDF of normal mu sigma squared, okay. So, clearly this y, see, you start with the standard normal 0 1. If you do the affine transformation sigma x plus mu, you get another normal distribution mu comma sigma squared. Okay, so this is a very nice property, right. So, for uniform also we had this property, you had a uniform PDF, you do a affine transformation, you get another uniform PDF. Normal also satisfies this property. You start with the normal, you do an affine transformation, you get another normal distribution. Okay. So, you can also sort of reverse it. Supposing you start with x being normal mu sigma squared, and then you do x minus mu by sigma, you will get normal 0 1. So, here is a normal distributed random variable with parameters mu and sigma square, and notice what I am doing here, this is also affine. Okay. So, this looks a little different, but this is y equals 1 by sigma x minus mu by sigma, isn't it? It is not any different from that. So, from here you plug in, instead of y, you replace y with y plus mu by sigma and the next by sigma. So, you will see you will get back your normal 0 1. So, this I will leave as an exercise to you, make sure you can do that, right. So, remember this is what this PDF is 1 by sigma root 2 pi e power minus x minus mu whole squared by 2 sigma squared, and then you are doing this transformation y equals 1 by sigma x minus mu by sigma. Okay. So, instead of x you have to replace with replace x with y plus mu by sigma by 1 by sigma, right, which is equal to sigma y plus mu. Okay. So, you replace x with sigma y plus mu, you will see that plus mu and minus mu cancel, you will get sigma squared y squared, the sigma square will cancel. Okay. And then you also have the 1 by mod a, right. So, 1 by sigma, that will cancel with the sigma, and you will get the normal 0 1. So, it is a small exercise, try this and convince yourself that it is true. Okay. So, the moral of the story is that the affine transformation of a normal random variable remains normal. The two parameters change, they change based on how you do the the affine transformation, but it remains another normal distribution. Same thing with uniform also, we saw that property, this is very good. Okay. Okay. So, I am going to do 3 illustrative examples. There are 3 problems, and you will get interesting little answers in the, and you will see, maybe I will do one more problem as well. So, there are 3 problems to illustrate how one can do computation for different types of functions. Okay. This is not meant to be exhaustive, just to give you a flavor of how other functions can be handled. So far we have seen some simple functions, affine seems like a very simple transformation. What about slightly non-trivial transformation? Okay. So, here is one example. So, you have exponential random variables. So, fx of x is lambda e power minus lambda x for x greater than 0, 0 otherwise. Okay. And you need to find the PDF of x squared. So, g of x equals x squared, And if you look at g of x, so remember support is what? Support is set of all x such that x is greater than 0, okay? And if you look at g of x here, in x greater than 0, it's monotonic. For x greater than 0, g of x is monotonic for x greater than 0, okay? So my formula applies, okay? So what is my formula? I need my g prime of x, which is 2x, okay? And then I need the inverse, right? So g of y equals x squared implies x is square root of y, positive square root of y, because x is greater than 0. So g inverse of y is square root of y, okay? So now one can use just, so if y is x squared, fy of y is just the formula 1 by 2 times square root of y, the PDF, which is lambda e power minus lambda times, instead of x you need root y, okay? So that's the PDF, and that's for y greater than 0, okay? So you see, this is just the formula. How did I get the formula, by the way? I mean, it's 1 by absolute value g prime g inverse of y times fx of g inverse of y, okay? So instead of x you put g inverse of y, which is root y, then 1 by g prime, which is 2x, and then g inverse of y, which is root y, okay? So that's all. It's a very simple formula. So the monotonic case, even if it were a monstrous function g of x, as long as it's monotonic, I know my formula applies. I just have to find the inverse, I have to find the derivative, close my eyes and plug in, I'm done, okay? That's a nice thing to know. Okay, so here's a slightly more twisted setup. X is uniform from minus 3 to 1. Okay, so let's say this is x and this is minus 3 to 1, and this is height would be 1 by 4, isn't it? So that's the height of the PDF. This is fx of x. Okay. So now I need to find the PDF of x squared. The problem now is, you know, the support is minus 3 to 1. And g of x equals x squared is not monotonic in support of x, right? If you were to plot x squared, you will have to do this, right? G of x should go like this. Sorry about that. So it will go like this. Okay, so I'm not drawing very much to scale, so maybe I should make this also a little bit better. So this is g of x equals x squared. Okay, so it's not very much to scale. Don't worry about the scale too much. Clearly, it's not monotonic in that range. In the previous case, in the exponential, it was only for x greater than 0, so it became monotonic. It was very nice. But here, it's minus 3 to 1. It's not monotonic. Once it's not monotonic, you can't use the formula. If you can't use the formula, you have to fall back to the traditional method of evaluating. Okay, so I'm going to take y in the range. So y, first of all, so y is x squared. So it belongs to 0, 9. Do you agree? Okay, so x is minus 3 to 1. So if you square it, you will get values from 0 to 9. Okay, so it's only positive. So if you take y from 0 to 9, fy of y is probability that y is less than or equal to small y. Okay, so this is probability that x squared is less than or equal to small y. Okay. So now interesting cases will come, right? So for instance, if if y were to be between 0 and 1, okay, x squared less than or equal to y is the same as x falling between root y and minus root y. Okay, so this is true for x being 0 to 1. See, remember 0 to 1, there is like minus 1, minus 2, minus 3. X has support on both sides, minus 1 to 1, right? So it's sort of got both sides going. So if you pick any y here, if you say x squared is less than y, then right? I'm sorry, y is not here. So why did I do this? So y, if y is here, let's say, let me just pick a y here, and then this would be root y, this would be minus root y. So if you want g of x to be less than or equal to y, then x is here, right, between minus root y and root y. Okay, so that's the picture that you have to draw. Okay, so you get this. Now on the other hand, if y is between 1 and 9, notice what happens. If y goes above 1, so for minus 1, so this is 1, right? So, oh, my picture is so badly out of scale. Okay, forget about this. So let's just get this going. So this has got to be, let me redraw this. It's okay, I should draw a good picture. So let me redraw this picture. It's okay, you can see in the video that I've redrawn this picture. It's a good picture to draw, so let me just draw this properly. So it's a question of getting the scale also, right? So you got 0, you got 1, and minus 3. Now this is going to be really tiny, 1 by 4. And then, so this 1 would come somewhere here, right? So this is okay, this is reasonably to scale, I think. And then if I draw g would go like this, right? So like that. And minus 1 would come here. Okay, this is reasonably to scale, I think it's okay. And g would go like this. This is g of x equals x squared. Okay, I think I've got it. So this is good. So if y were to be between 0 to 1 and 0 to 1, so you will have root y and minus root y both occurring here. So if y goes above 1, y goes here, when it goes above 1, square root of y and minus square root of y is not going to work out, right? So it can go all the way up to like 9, isn't it? Okay, takes any value there. Root y, if it above 1, it will go to the right of 1. So x squared less than or equal to y may fall between minus root y less than x minus less than root y, but you don't need the all the way to root y here. It's enough if you do 1. Okay, why is that? Because if I mean root y after 1 it anyway becomes 0, right? So it's enough if you do this. So the probability fy of y, which implies fy of y, is this height is 1 by 4, by the way. So it is 2 root y by 4, right, times 1 by 4. So in this case, fy of y will be 1 plus root y, not 2 root y. It's 1 plus root y by 4. Okay. So it's root y by 2 and then 1 plus root y by 4. This is the CDF, isn't it? So if you were to do the PDF, you can also do the PDF if you like. If you were to do the PDF, you're going to get 1 by 2 times root y is 1 by 2 root y for y between 0 and 1, and then 1 by 4 times 1 by 2 root y for y between 1 and 9. Okay, so this is the PDF for y. Okay, so notice when you had a uniform distribution minus 3 to 1 and then I did y equals x squared, I'm getting a strange distribution, isn't it? The CDF ends up being a square root of y, sort of behaves like that, and then the PDF will be 1 by 2 square root of y. Okay, so you'll start getting strange looking PDFs. You started with a uniform PDF, and because you did this nonlinear transformation of x squared and you go through the calculation very carefully, you notice the care with which you have to do this calculation. See that you have to carefully look at one value of y at different ranges and how that translates into that set AY, isn't it? The set changes from one to the other depending on the range. You have to do a little bit more care here, but it's not very tough as such, but you have to pay attention. You have to pay attention to this detail of where it exceeds 1, where it does not exceed 1. It's a bit more difficult. I mean, when the formula applies, it's so nice and simple. when the formula doesn't apply, if it's not monotonic, it's a little bit more care that is needed. But if you practice a little bit, think of different cases where such methods are used, you'll get to the answer. Okay, so this is the CDF and PDF for x squared, of squaring of a uniform distribution. Okay, so now here is an odd looking function. X is uniform from -3 to 1, and my g of x is max of x comma 0. Okay, so notice this g of x is max of x comma 0. So what is max of x comma 0? What is the meaning of this? So one way to think of it is 0 if x is negative. X is between -3 and 0, and it is x if x is between 0 and 1. Okay, so if you restrict to the support of x, so if you say x is in the support of capital X, which is actually -3, 1. Okay, so notice max of x comma 0. If x is negative, the maximum is always going to evaluate to 0. If x is positive, it is going to evaluate to x. Okay, so it's a strange looking function. I mean, it's not so comfortable to work with this function. So if you were to say y is g of x, and then y belongs to what? It belongs to the set 0, 1, right? It takes the value 0, and it also takes values up to 1. Okay, so that's the range of values. Okay, now notice what happens here. So this is clearly not a easy function to deal with. It's not differentiable and all that in the way we know it. At least at 0, it seems to have a problem with differentiation. We don't know how to deal with such cases very easily. So maybe you should go back to the CDF method. Okay, whenever you have these kind of functions where it takes a constant value. So if you want, you can plot this. Actually, it's not very hard to plot. G of x. It takes 0 for negative values, and then it goes to x up to 1. Okay, so it's a easy function in some sense, but the fact that it stays 0 for so long and it picks up here, it's not differentiable here. So my wonderful, and it's not also invertible and all that. So this is, when I say monotonic, it needs to be strictly monotonic, as in it's increasing or decreasing. This is staying constant for a long time, and all that is not very, nice for my formula. So my formula won't work. I have to go back to my previous method. So now here you notice there is something strange about y equals 0. Okay, when y is 0, notice what happens. Fy of y is probability that y is less than or equal to 0. Okay, so if y has to be g of x is less than or equal to 0. Okay, what is the range of x for which this is going to happen? This is the same as g of x less than or equal to 0. It never goes negative, right? It's always equal to 0. So this is the same as x lying between -3 and 1. Then 0. Do you agree? If x were to lie between -3 and 0, then y will be 0. Okay. If not, y will not be 0. So probability that y is less than or equal to 0, it's the same as probability that it's actually equal to probability that y is equal to 0. I can write like this: g of x is equal to 0, and that's the same as probability x being -3 and 0, right? X between -3 and 0. So that comes out as 3/4. Okay. Notice that strange thing once again. So you're getting Fy of y, probability that y is less than or equal to 0, to be 3/4. Now if y were to be less than 0, what will happen? If y is less than 0, Fy of y, probability that y is less than or equal to a negative number is actually 0. Okay. So keep that in mind. So if y is less than 0, it's 0. At 0, there is a jump in the CDF. Okay. So whenever you have a flat part in your function, okay, you have a support of the random variable, and you have a flat part in your function. So that value is being taken with a non-zero probability because of the function. Okay, so in this function takes a value 0 over the entire set of values minus 3 to 0. Okay, so whenever x falls in the interval minus 3 to 0, my y becomes equal to 0. So the probability that y equals 0 is actually 3 by 4. So immediately this tells you that y is not continuous. Okay, so it's not a continuous random variable. So if you take some transformation like this, max of x comma 0 and all that, you can expect that the output you get a random variable which is not even continuous. Okay, so this kind of thing can happen. Okay, now you can also do for y between 0 and 1. Okay, you can evaluate fy of y. You will get 3 by 4 plus y. Okay, so I'll leave this as an exercise. You can check that 3 by 4 plus y. Okay, so if you were to plot fy of y, you get the 0 here, and then there is a jump to 3 by 4. Okay, just hold on. So this y by 4. I'm sorry. Somewhere I thought I made a mistake here. So y between 0 and 1, fy of y. This is an exercise. I'll leave you to check it. It's not very hard, but you need to do some work here. Okay, so fy of y is 3 by 4, and then it goes up to 1. Okay, so it goes up to 1 at 1, and then it stays at 1. Okay, so for y greater than 1, fy of y equals 1. Okay, so this is what happens here. So and you get a mixture here which is not a continuous distribution. Okay, so you see there is a jump, and then there's also a part where it's increasing. It's not purely a discrete distribution. It's a mixture distribution. Okay, so this can happen. So go through this steps and how I did it very carefully. The crucial part is the function g of x stays a constant for an interval inside the support. Okay, so inside the support of your random variable, for an interval, if g of x is staying a constant, that particular constant value can be taken with non-zero probability. Okay, so in this case, y equals 0 gets taken with probability 3 by 4. It's non-zero probability. So you don't get a continuous random variable. Okay, so this can happen. In fact, you can quite easily cook up functions which will give you a discrete PMF as the output. Okay, so supposing let's say I have a g of x which is like this, right? G of x, let's say minus 3 by 2, 0, and then 1. Let's say it is like this, a function like this, right? Okay, so you can put your little things here if you like, right? Doesn't matter where you do this. Okay, so if it were a function like this, supposing you have g of x and x is uniform from minus 3 to 1, and g of x takes value, I don't know, this you can put as 1 by 3, 2 by 3, and 1. Okay, now if you look at, I don't know, maybe I'll call it g1 of x. Okay, so if you define y1 as g1 of x, this is actually a discrete random variable. Okay, so your random variable, your function, the transformation g of x takes only 3 values. It takes only 1 by 3 or 2 by 3 or 1. And what's the probability with which it takes it? You can easily calculate based on the, going from the interval to the interval of x. Okay, and then you'll get it. Okay, so just do the inversion very carefully, you will get it. So by choosing your function g, you can make a random variable, a continuous random variable into a discrete random variable. You can make a continuous random variable into a mixture. You can keep it as continuous also. Okay, so this thing is sometimes important. Sometimes you will have a function like max of x comma 0, particularly taking maximum. It happens quite often, right? And the 0 might be a threshold. You may only worry about what happens above 0 and all that. So all these things can happen. So what is the moral of the story here? The big moral is what I told at the end. Okay, so you can do a function a transformation of a continuous random variable, if it is simple enough, if it's monotonic, differentiable, right, as an inverse, as only one inverse, it's very easy, there is a formula. And continuous remains continuous. But in many other cases, if the function is flat for a while and it jumps here, there and all that, then you can get all sorts of strange answers. You can get, you can get continuous also. You can also get discrete, you can get mixtures also. Okay, so transformations of random variables is a very interesting and exciting thing. And the one method that always works is that CDF method. You try to find the CDF, do the inverse of the function, look at all the values of x for which g of x is less than or equal to y, find the probability of that. That always works. It's a bit laborious, you have to pay a lot of attention, be very careful, but that's a method that always will give you the correct answer. Okay, so that's the end of this lecture. Thank you very much.